Hi, this is Jose Luis, and welcome to another geometry gem. This one is a continuation of the two previous ones where we were solving the problem of fitting a bunch of spheres along a curve, right? But for this one, it's going to be a little special because what I'm going to try to do here is I'm going to try to pack as many constraints in this algorithm as possible. Those constraints being controlling the amount of spheres that I'm going to fit the curve with. I'm going to constrain them so that they're perfectly tangent to each other, so that there are no overlaps. And on top of that, I want to be able to make sure that the radius of the sphere is enough so that these spheres fit all along the curve as perfectly as possible with the least amount of remaining distance here at the end. The problem with all these constraints is that there are so many that there is no closed form. There is no one deterministic algorithm that I can use to pack all these constraints together. So what we're going to do is I'm going to be using Galapagos, which is a genetic evolutionary solver inside of Grasshopper. I'm going to use it to basically go over all the possible values of the diameter and find the one that is the most optimized to satisfy all these constraints that I just explained. And I'm going to show it working here. So you can see that right now what I do have, you can see that right now Galapagos is trying to optimize and is going through trying like many different iterations of the diameter, and is trying to find one where it gives me 15 spheres, and is trying to get this distance as small as possible. And you can see that over time, the more it tries, is converging to a better solution here, one that is giving me a very small distance here by the end. I think this is a really interesting exercise to do because it involves optimization, and it involves thinking about what's called a fitness criteria. So how do we generate a value that we use for the solver to optimize, to either minimize or to maximize? I'm going to pick it up where I left on the 2 gems ago, where I implemented these algorithms in vanilla Grasshopper. I'm going to pick it up from them. And because this is also the first optimization slash Galapagos video that I'm recording, I'm going to be perhaps a bit slower, and I'm going to stop in all the stages of the process and explain them very carefully, because I want to make sure that we understand everything that is happening. Hopefully at some point in the future, if you're watching this from the future, there will be an optimization playlist at some point, but it doesn't exist right now. So I'm using this gem to almost as an excuse to do my first introduction to genetic optimization. Okay, it's going to be a super interesting one if you're interested in optimization, and it's going to be a fairly easy one to implement. So stay with me, and let's get hands-on. Woohoo! Well, first of all, what I would like to do before we start is to actually make sure that we understand the problem that we're trying to solve, that we understand it very clearly. And I would like to remind you that we're coming from 2 videos ago where we solved the problem of trying to populate a curve with a bunch of spheres. And we did it using vanilla Grasshopper, and we did it in 2 different ways. First one was we developed an algorithm where we could control the number of spheres, right? And because we subdivided the curve in an amount of segments where the length, the chord segment between them was equal, then we knew that that like all the spheres did fit perfectly inside of the curve. So the last sphere, the center of the last sphere, was at the end of this curve, right? The problem with this algorithm is that because we are using equal chord length of the curve, when that segment of the curve is very curvy, when it's very concave, we have the problem of spheres overlapping each other. So you see this overlap here, and you see this overlap here. So that is not great if we're trying to model something that needs to be physically more accurate, for example, right? So we did develop this other algorithm where what we did was instead we did control the diameter of these spheres, and then what this component does internally is it places one sphere, it computes the intersection, it finds that, and then it places the other sphere and then the next sphere, therefore guaranteeing that all these spheres are perfectly tangent with each sphere is perfectly tangent with its neighbors, right? The problem with this one is that because we are controlling the diameter and we are controlling this perfect tangency, we are not guaranteed, first of all, how many spheres do we have. So the smaller the diameter, obviously, the more spheres we have on the curve. And on top of that, we're also not guaranteed that the last sphere, the center of the last sphere, is going to land at the exact end of the curve. Because since this is whatever diameter, then this sphere can end anywhere, basically. So what we're trying to solve here is we're trying to combine more of these constraints. And what I would like to try to do is implement something where we can control the number of spheres, okay? I'm interested in controlling the amount of circles. I'm also interested in the fact that these spheres must be perfectly tangent to each other. And on top of that, I also want to make sure that I minimize this distance and that the last sphere is as close as possible to the end of the curve. All of those things together, all of those constraints together, there is no closed form solution that I can use to reach that solution. And the problem with that is that because that where this sphere lands at the end of the curve depends very strongly on the shape of the curve. The way to compute that algorithmically would be very complex, if it's even possible, which I'm honestly not very sure that it is. Okay, so what we're going to do is we're going to follow an optimization process. We're going to implement an optimization algorithm, which what it basically does is we're going to try a lot of different values of the diameter. So we're going to write an algorithm that is going to basically start throwing a lot of different dices. It's going to start going through all different ranges of values for the diameter, all right? It's going to check first if we have the right amount of spheres, and then it's going to check if the distance between the last sphere and the endpoint of the curve is as close as possible to zero. And the more values we try, the more we will find one of these values for the diameter that will satisfy both the number of spheres that we want and the fact that this last sphere is as close as possible to the end curve. This is what we're going to try, and we're going to try that by using Galapagos, which is a genetic optimizer that is built into Grasshopper. Galapagos will give us the possibility of pointing to what is the parameter that we want to explore. So what is the range of values and the parameter that we want to explore? And then what is the fitness criteria that we want to implement? Fitness criteria is that situation, that value, that result that we want to optimize. And I will explain how that works in a second, okay? So I think we're ready. If that was clear, I think we are ready to get hands-on and to start implementing, to start building towards that implementation, okay? So let's get hands-on. Let's start by the beginning. So what I'm going to do is I'm going to take it off from the gem where I implemented this algorithm in vanilla Grasshopper. And then I'm going to remove all of this because all of this is the algorithm that gave me overlaps, and that's not what I want. I want perfect tangency. So I'm going to start building off from this part here where given the diameter of the sphere, I get all these spheres populated on top of the curve, right? And then because I'm going to be, the thing that I want to optimize is that these spheres, the last one must be as close as possible to the end of the curve. First of all, the one thing that I will need to do is I will need to calculate that distance, the distance between the last element and the end of the curve. I'm not going to do Euclidean distance. Well, let me do Euclidean distance to start with. So the thing that I would do is I would take this list of points. I would take the last point of this list. So I would say, for example, I would say, let me do list item, and then from this list, I'm going to take the last element, and in Grasshopper, you can, if you wrap the list, if you do -1, you can, if you do -1, then basically -1 means the last element starting from the end of the, so if I go here, you can see that the last one is 13, 24, blah, 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 and this is the one that I have here. So this is the last element on the list, all right? So this is the last point where I divide the curve. Now, I also can take from the curve, there is the endpoints component that gives me, from a curve, it gives me the starting point and the end point, okay? So I could calculate the Euclidean distance, the physical distance between these two. And you know what? I'm actually going to start with that, but I will explain in a second why this is not what I really want to do. We will get there. So this distance is the parameter that I want to optimize. And by optimizing, what I mean is that I want to make sure that when I start trying different diameters for these spheres, this value is as close as possible to 0. That would mean that this sphere will be as close as possible to the end of the curve, right? And I think with this, at a very basic level, I'm already ready to start implementing a basic test, Galapagos test, because I have what I want to optimize. I have the diameter of the spheres, and I also have the fitness criteria. The fitness criteria is the one value that I want to either maximize or minimize, the one value that I want to make as large as possible or as small as possible. And in our case, it's going to be this one, the distance between the center of the last sphere and the last point of the curve. So I'm going to drop here a Galapagos solver. This is here under utils. You can just plug in Galapagos and you can see that there are, because this is an evolutionary solver, everything is phrased in terms of genome, fitness criteria, gene pool, etc., evolution. So, but it's actually much more simple than it sounds. So there are two things that I want to control. First is the genome, and the genome is how Galapagos refers to the value that I want to explore so that I can find an optimal solution for that value. In this case, that's going to be our slider for the diameter. So this is the value that I would like Galapagos to start exploring and finding like a lot of different values and computing those results. And the fitness criteria is going to be this value here, the distance, because what I will want is to tell Galapagos that this distance has to be as small as possible. So whenever Galapagos starts messing with the value of the diameter, Galapagos is going to start reading the value of this distance. And it's going to try to find values for the diameter that make this distance as small as possible. That's the basics of how Galapagos works. So I can double click here right now, and you can see that in the editor, I have a lot of options. I'm not going to get into this at all. I have some links to blog posts by David Rutten, the author of Grasshopper and the author of Galapagos as well. These blog posts are actually really, really nicely explained, and they have really good graphics and really good illustrations. So if you're interested in this topic, I really recommend that you check this out. The only thing that I would like to touch here, which is very important, is the fact that for the fitness, I have two options: maximizing the fitness or minimizing the fitness. In this case, I want to click on minimize because I want this value, the distance, to be as close as possible. If it was the other way around, if I wanted some value to be maximized, then that's what I would click. And then I'm going to click here on solvers. Solvers is the area that gives me access to two different solvers, the evolutionary one and the simulated annealing one. I'm also not going to get into the weeds of how they work or how they're different. I will get to that at some point in the future. And then here is the Start Solver button. Let me first save this file because I believe we may run into performance and crashing issues. So let me do that, and then when we go to solver, I'm going to try my first run at solving this. So I'm going to. How can I? I'm going to. Yes, I'm going to double click here. I'm going to put this here. I'm going to put the solvers here, and I'm going to hit start solver. And what we're going to see is that Galapagos is going to start messing with the values of the diameter. So you can see that Galapagos right now is trying a lot of different values for the diameter, and is reading here from the distance what distance is getting, right? But you can see that my computer is starting to be not very responsive, and I actually believe that we will probably crash very soon. Is that true? Are we crashing? Crash, 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 crash. Crash, 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 crash. Oh, it is crashing. Poor Galapagos. Oh, it's back. It's back. Well, I'm going to stop this. I'm going to stop this, and you see it's not being very responsive right now. I'm going to stop this because there are a couple things that I will need to change here. Okay? And I will explain why this is not. Oh, it crashed. Oh no. All right, so you see, I'm going to need to restart. Let me restart and I'll get back to you in a second, okay? Okay, we're back. It didn't hurt, the crashing didn't hurt that much. It's okay. I have a different curve because I didn't save this file, but it's fine. So why did we crash? Well, when we do optimization can be a fairly computationally expensive process. So if we also have other computationally expensive processes are part of the optimization, then things get very expensive, really. And one of the problems that I was having was that this slider here, the one that we are trying to optimize, I didn't really take good care of making sure that the boundaries, the range of this slider was good for an optimization routine. And what do I mean by that? Right now, the slider, so the value of the diameter could range anywhere from 0 to 10. And look at what happens if Galapagos starts going into values that are on the lower range of this slider. So if the value of the diameter starts getting smaller, you can see that the divide distance component starts getting more expensive. What I have here is is the profiler, which is giving me the computational time that this component takes to compute these values. And this component is particularly expensive just because the way it works is that it does one sphere at a time. It computes the intersection of the one sphere with the curve, and it uses that to generate the center of the next sphere. So it's an iterative process that uses intersections between surfaces and curves, which is a fairly expensive operation. So that's why as I go smaller with the diameter, you can see that the value, the computation that it takes this component to execute, it just increases a lot. And right now it's blocked. You can see it took for this diameter, it took almost a full second to execute, right? And then if I go even smaller, like something, for example, 0.1, I think I may actually crash it again, but it will definitely take exponentially. You see, I'm crashing it again. No. Did we solve? Oh yeah, it solved. It took 10 seconds to compute this operation, and also to render like however many hundreds of spheres there are here. Is also a fairly expensive operation. So Galapagos was crashing because it was requesting very expensive operations due to the range that we had set for this slider. So one way to solve that is to constrain the parameter space that Galapagos can use to explore this particular value. So for example, instead of, and you can see that because we have 0, the closer we get to 0, the exponential growth in computational time, which could even lead to infinity, right? So let's bound that. Let's say that, for example, we're going to have like the minimum value of the diameter is going to be 2, and the maximum value is going to be, there's going to be no bound for that. It's going to be 100. We don't care, right? But as we do that, you see that the minimum boundary now for 2 is something that is, for the scale of our curve, is something that is reasonable. So, so Galapagos is going to have a much easier time now dealing with this. So for example, I think now we are ready to give it another go. So I'm going to double click here, and I'm going to keep minimize here, and I'm going to use the default evolutionary solver, and I'm going to start solving. And you can see that Galapagos now has a much easier time switching between values. It doesn't get stuck on a one value that requires a lot of computation, right? And you can see this is very nice. You can see how Galapagos now is basically exploring, and the interface is really nice for this. It's basically exploring like a lot of different combinations of this value of the diameter, right? And it's trying to find the ones that give us a smaller value for that distance between the last sphere, the center of the last sphere, and the center of the last point. And you can see that right now it's actually reached a very optimal solution, one that is only 0.01 units away from the end of the curve. That's another thing with optimization, with genetic optimization. Very often you don't get an exact result. It's very likely that we're not going to find a result that is going to give us 0 as the distance between them, just because it's we're trying to get an approximation by doing heuristics, is the technical word, by doing a lot of tests and trials, and then finding one solution that is optimal. And something very interesting happened here, which is what I want to talk about right now. You can see that if I stop the solver now, the solver found a solution that is even closer to the one that I was showing before, 0.004 units away. So if I zoom in here, they're like so close to each other. Not quite perfect, but good enough. All right, this is how optimization is. It doesn't get perfect, it gets just good enough. But the funny thing is that it found it. I don't know if you remember, but for this solution, for this solution, we had a much larger number of spheres than for the solution that we're seeing right now. And I would venture to say that, and the reason for this is that right now, the way we have set all of these, we are finding a solution where the sphere is as close as possible to the end. But right now, for example, the one that Galapagos converged into, instead of having 15 spheres, it has 18. And if I were to just move this value around and run the optimization again, then it will probably end up converging into another solution that is also very close, that has the last sphere very close to the end, but it's also not 15. You see, for example, it already found one, now it found another one that is a bit closer, now another one that is a little closer. And if I were to stop here, for example, you can see that the result now is like 29 spheres. The problem here is that now we're getting close to what we want, a perfectly fit set of spheres that are tangent to each other and fit the curve very nicely, but we are not optimizing at all for the amount of pearls. We're not anywhere here in the algorithm, we're not specifying that we actually want a control amount of spheres. And so how could we make that happen? Well, we have to understand that because Galapagos is just finding random diameters, among that randomness, whenever it finds a diameter that gives whatever combination of number of spheres, but a good fit on the curve, that's where it converges, right? So what we need to do is we need to somehow, in this process, make sure that the amount of spheres that we want is accounted for in two different ways, as a minimum range, but also as a maximum range. So there are a couple things that I would like to do now then. And the first one is going to be, first of all, to discard all the solutions that give me spheres above the ones that I want. I'm going to discard all the solutions that give me more spheres than the number that I do want as a target. Okay, so let me show you how to do that. As you can see right now, when we calculate for a particular diameter, when we calculate the amount of divisions of this curve, we're basically letting Grasshopper, if it gives me more than the divisions, the number of spheres that I want, if it gives me more, I'm just letting it use that many spheres as part of the calculations for fitness. So it's just populating all those points with spheres, and then it's using those for calculations. So that is the first thing that I will need to fix. If when I do divide distance, I get more points than the amount of spheres that I want, then I will need to remove those points from the calculation and then just stick to the first 15 that I want to calculate. So how can I do that? Well, I think it's as easy as taking, for example, all the list of points that I'm getting from this computation, okay? Taking that list of points and splitting the list in two with a split list component, splitting the list in two, and at the index number 15, which is going to give me here at A, is going to give me the first 15 objects, and then in B is going to give me the rest, which I'm just not going to use. So if I plug these 15 objects here, and if I plug them into this list here, then you can see that now I have basically discarded all the points that were beyond my first 15 spheres, and therefore when I calculate the distance, now this value is very large, right? So you can see that now this value, if I make this very small, this value is very large. So Galapagos is going to pick that up very fast, and it's going to start finding values that are closer to you. So let me start now the calculation with the minimum radius, the value of 2. So for example, here I'm going to now run the calculation, and I'm going to run the solver, and let's see what happens. I start solving, and then you can see that immediately it finds a larger value, right? And it found an optimal solution with 2 spheres. Now with 6 spheres. And if we let it run a little longer, it will probably find some other more fit solution. Oh, again with 2 spheres. I mean, this is true. 2 spheres are fitting perfectly now on the curve. But you see, so what we've done is we have managed to find a solution that is under the amount of spheres. Okay, but so we have been able to penalize the fitness criteria if it gave me a solution that had way too many spheres on the curve, right? I find it really funny that it has found like a very, very nice solution for 2 spheres right now. So what we would need to do now is we would need to find a way to penalize also the fitness criteria if it is giving me too few spheres. If it gives me a solution like this one, for example, where if it gives me a solution where we only have 2 spheres, I need to be able to somehow artificially increase this value a lot so that Galapagos thinks that this is not an optimal solution. Okay, and this relates to the problem that I was saying before, and the fact that I'm not very happy with the fitness criteria being the Euclidean distance between the center of the last sphere and the end of the curve. Because think about this. It could happen that if this is what I'm using, it could happen that if I take this curve and I take this point here and I put it somewhere very, very close on top of the curve, it could happen that as I am, for example, here, right? It could happen that Galapagos could find a solution where it could populate all of this with spheres all the way until here without actually closing the loop, just because the Euclidean distance at some point here is very small. Let's try this. Let's hope we get some luck and we find something like that. You see? We did. So we are now converging to a solution where the last point is actually very close to the end point of the curve, but not in the way that we want, not fulfilling all the curve. So for me, Euclidean distance is not a great measure of what I want to do. So how can we change this? What I would propose to do is, instead of using Euclidean distance, what I would like to use is I would like to use the domain of the curve. What does that mean? If you've seen my other videos, you know that curves have this thing called the internal domain. So for example, I'm going to say domain here, I'm going to deconstruct the domain, and if I plug in this curve here, you can see that the curve starts at 0 and ends at 64. Domains have this, curves have this thing called the domain, which is basically a measure of the internal length of the curve. It's not exactly length in terms of world units. It's more of it's a concept that is not very straightforward, but it's basically how the internal points of the curve are distributed along that curve. But the main takeaway here is that we can measure where we are along a curve, both in the length of the curve, in the length of the chord of that length, but also we can measure as in which parameter are we along the curve. So the parameter being that value between 0 and, in this case for this curve, 64.41, which again, this is not the length of the curve, this is the domain range of that curve. So if we say I want a value whose parameter is on this curve at, for example, 10, then it will probably give me a point somewhere around here, okay? And we also know that this point here, the end point of the curve, is at the parameter 64.41, whatever, of this curve. Which means that I can measure, for points, I can measure where I am along a curve by finding the parameter of that point on top of that curve and computing how far along that curve I am, right? So how can I do that? If I take this point here, the last point that the last point of my subdivisions, what I can do is I can say, can you find what is the closest point for this point to the curve? All right, and that point is probably going to be, because that point was on the curve, is going to be the exact same point, right? But this component also gives me this other thing called t, which is the parameter on the curve domain of this closest point. You can see that right now is 38, which is kind of halfway between 0 and 64. And if I start cranking this up, and if I try to bring it all the way very close to the endpoint, you can see that this parameter right now is going to be 62 point something, which is very, very close to 64. So I think using the parameter of the center of the last sphere and the parameter of the endpoint of the curve is a much better way of finding a fitness criteria for these two. And what I'm going to do is I'm going to subtract this, and I'm going to say the value of, if I subtract the value of the parameter at the end of the curve, okay, with the value of the parameter of the last point of the sphere, this value right now is like 1.4 something something. If I make this varies, if I reduce the radius, you can see that this value is much larger. But if I crank this up so that this is closer, this value becomes much smaller. So this is a really good candidate now for optimization. We're going to optimize the difference in parameter between the center of the last sphere and the endpoint. And proof of that is going to be that if I now do the same thing as I did before, if I put this point on top of the curve and I move this all the way back to 0, then if I now try to optimize, I don't think this is going to get stuck on a solution that has spheres ending up here. You can see that it got stuck on these like 7 spheres, but it's pushing the spheres as much as possible to the end of the curve. It's not getting stuck here. So I think curve domain is a better approach. And so we are now on a better position, but we still have the problem that we are not going to find a solution that gives us more spheres than the ones that we want. But we may find a solution like we just did right now that is giving us less spheres than the ones that we want. So what we need to do now is we need to find a way to penalize the fitness criteria if the spheres are less than the ones that we are targeting. And I think for that, I'm going to have to draw a diagram to explain that concept. So let me get into the whiteboard. Okay, so let's imagine we have our curve, all right, and then that we apply the subdivision algorithm, and then we end up with some points on top of the curve, and then we know that the domain of the curve goes from 0 to 64, for example, or whatever in this case. So we know that what we're doing right now is we're calculating the distance between this domain here and the last domain of the last point. So this might be, for example, 1.3, blah, 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 whatever, in domain space, not the Euclidean distance, right? Remember the domain in parameter space. The problem with our algorithm is that we are computing this parameter distance no matter how many points we have here, whether if those are 2, 3, 15, or whatever. It's just the result of the diameter of the spheres. We fit however many spheres, and then we calculate that. So Galapagos is not making any difference whether if here we have 3, 10, or any amount. So what we need to do is we need to somehow make sure that this value is also representing the fact that we may have more or less spheres than what we want. And what we can do is we're going to do like a trick. And the trick that we're going to do is that we're going to imagine that we were to continue this curve and to actually fit the exact number of spheres that we wanted. Okay? What does that mean? Imagine that here we have, for example, 7 or 10 spheres, but we actually wanted 15. So we can imagine, for example, that we extended the curve and that we actually extended the algorithm and we kept populating this curve with however many spheres. The idea would be that the last sphere will end up somewhere in the parameter space with a value that is actually much larger than what the domain of the curve can hold. So if we were able to find out what this number is and then use this distance as the fitness criteria, this would be like 23 point something, something, something. That would mean that because that number is so large, then Galapagos will try to reduce this number, therefore starting to fit all those 15 spheres closer and smaller inside of the domain of the curve. All right? So, and this would only happen when we have less spheres here than the amount that we have. When we have, yeah, you understood that. Now, the problem is that we cannot really extend the curve, and we cannot really populate that extension with more points. If we were to do that, it would be a very expensive operation, and it doesn't really make sense. So what we want is to actually find a way to artificially cheat Galapagos and feed Galapagos a value of the domain of the last point here that is not exactly the one of the real point that we have found, the real point being one that is less than the amount of spheres, but one that has been artificially increased to reflect this imaginary notion of us extending this subdivision beyond the boundary of the domain of the curve. All right? And how can we do that? We can actually do that with a very simple numerical rule. Because if we say, for example, let's say that the domain of the curve goes all the way to 64. All right? And let's say that for a particular radius, so for example, for the radius of 3, what we got was 7. We got 7 spheres here inside of the domain, right? what that means is that proportionally, more or less, we can think that if we had gotten a radius that had given, for the same radius, if we could subdivide like a longer curve and get actually 15 points, the ones that we want, more or less, we can estimate that the domain at which we would end would probably be roughly double what we have right now. Because this is 64 and 7 is roughly half 14, we can estimate that more or less we would end at that, for that particular radius, we would end at a domain that would be at 120, for example. If we do that estimation, then Galapagos would understand that the radius of 3 is too large because it's giving it a value of the domain for 120, and then when you subtract that from 64, then it gives it like a really large number, and then it's going to try to reduce that number. Okay? So, what I'm trying to say with this is that we can perform a proportional rule where we say, given the amount of spheres that the algorithm is giving me for a particular radius, I can estimate for the total amount that I want, I can estimate where the domain of the last point would land in an imaginary curve that will be extending infinitely. And if I estimate that number, and that is the value that I use for calculations for fitness, then Galapagos will understand that for that particular radius, the last imaginary point would end up too far away and then would start constraining the radius, making it smaller and therefore fitting that imaginary sphere closer to the end of the actual curve. I hope this idea was clear because it was very tedious to explain, but you're going to see how numerically actually on Grasshopper and Galapagos is super easy to implement. So let's give it a try and see how this looks actually as an implementation. Okay, so back here, I have chosen manually a diameter that is giving me 7 spheres, okay, which we know that is roughly roughly half the amount that we actually want, because we want 15, right? So we can make a very simple proportional rule and say, I'm going to divide the number 15 by the number of spheres that we actually have. And the result of that is going to be like 2 point something, 2.1, because 15 is a bit bigger than 2 times 7, right? And if I now take the parameter of the last point, so this is 63 point something something, and if you remember the curve ends at 64, blah blah blah. If I take that number and I multiply it by, if I multiply that number of the parameter by this proportional rule, what you can see is that what I'm ending up with is with this value of the domain 136, which is an estimation of where that an imaginary sphere, the 15th sphere, would land on a curve that would extend here, blah, 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 infinitely, if we stuck to this diameter. It's not exact because we don't really have that curve. It's just an estimation, right? But because we have this really large number now, this really large number is an estimation of where that sphere will end up with, and because it's so large, then you can see that it's giving me a very large number here, which I think is a good indication for Galapagos to understand that this is not going well, that this diameter here is too big and that it needs to reduce it so that this value becomes as close as 0 as possible. So this is what I meant with, it's much more complicated to explain than to actually, because it's literally just one division and one multiplication. But let's run Galapagos now and see if this is going to work, which is not, and actually let me save things around in case it crashes. It's not going to work, but I think it's, so see what's going to happen. Galapagos is going to start solving, but it's going to end up converging always into a value that is close to 2 spheres. And wait, how is that possible? Let me wrap again. Let me go back to this minimum value. If I try that again, and I try solving again, it's also going to start and explode and become, and also converge into a solution that is just 2 spheres. It's the least amount of spheres as possible. Why is that? Because we have skipped something, a concept that is very important. And remember when I said that the Galapagos is trying to optimize for minimizing a fitness criteria? So what we have here is that because we have artificially increased the domain where the last point ends, this value of this abstraction can actually be negative. And what happens is that negative is actually a more minimal value than 0. So Galapagos tries to go as far down in the negative space as possible, because negative is less than 0. So it's more minimized in a way, right? So that's why Galapagos is always trying to get the most negative value here, which ends up being the one that has this imaginary sphere as far as possible on space, which ends up with us just having 2 spheres here on the real curve, right? So how can we solve that? Well, then it's actually very easy. So we can just calculate, instead of leaving this value signed so that it fluctuates between very positive and very negative, we can calculate the absolute value so that minus 405 becomes positive 405, which is a really bad value for the fitness, which Galapagos will try to reduce to the value of 0, which is as small as you can go for an absolute value. And I don't want to disclose anything, but as we click here and we click on the optimizer and we start solving, you can see that we have now converged to a solution that is a pretty good solution. It's at 0.07 parameter space units from the end of the curve. And if I stop this, I can probably see that it's got 15 spheres, and I can zoom in and see that this value is very close. If I now start from another value that is probably like very large, like 1 sphere, I can also see that if I start the optimization process and I start trying to solve, the solver is going to reduce this number very fast. And I believe we are probably now at 15. No, we are not at 15 yet. We are at 15 now, I believe, yes. And we are getting closer here. I can't zoom in here. I can only zoom. Oh, yeah, I can zoom. I can zoom here, yes. And if I stop, you can see that we are at 15, and we are also pretty close. I could leave this running a little longer, and we will probably find a value that is closer to the end. But I think with this, we have basically solved everything. Let me see. Yep, it did find a better value, or now a much better value even. So if I stop and I press OK, you can see that we're all super close. And again, with optimization, there's a compromise between computation and a fitness criteria, and we know that very likely we will not hit a perfect solution. We will hit a very optimal one, but not one that gives us 0 as the remaining parameter distance here for the curve. Okay, so I think with that, this is everything that I wanted to explain today. I hope that by purposefully having run into all the possible problems that we could run and all the possible things that could go wrong while we implement this, I hope to have made a good point, first at explaining conceptually how genetic optimization works, but also at making sure that we understand the concepts underlying them and how we need to do some numerical manipulation to make sure that the optimization, the solving process always stays within the boundaries, but also it gives us solutions that are constrained in the parameter that we're trying to solve. This was the first video that I have recorded in this channel about optimization and with Galapagos. So maybe that's why I took a little longer to explain certain stuff, but hopefully I will at some point record a series of a playlist or something with like more in-depth, like what is Galapagos? What are the options? What are the different solvers? And like a series of different examples that explain how different things affect different, basically an optimization playlist with a lot of, where I explain more in detail on the underlying concepts. In the meantime, I hope you liked this video. If you did, please click subscribe and hit the bell button and like the video and all those things. It just helps me keep the culture growing. And until then, thank you very much for being here. Check the other videos on the channel and see you soon.